How do you find the parametric solution of a dependent system? Imagine trying to find all the solutions to a puzzle where some pieces are connected in a way that they move together. That's what a dependent system of equations is like. These systems don't give you just one answer but many, forming a whole family of solutions. When dealing with nonlinear equations and functions, or systems of equations, dependent systems show a special kind of relationship. They are called dependent because the equations are not independent. They are linked in a way that one can be written as a combination of others. To find the parametric solution, you start by rewriting the system in matrix form. Think of this as organizing all the equations into a table. Then you perform row operations, like adding, subtracting, or swapping rows, to simplify the matrix. The goal is to get it into a form called reduced row echelon form. This step helps you see which variables are dependent and which are free. Variables that don't have a leading one in their column are called free variables. These are the ones you can assign any value to, acting as parameters. Next, you solve for the dependent variables in terms of these free variables. For example, if you have 3 variables and one is free, you might express the other 2 as functions of that free variable. Suppose you choose the free variable to be t, you might find that x equals to plus 3 times t, y equals 1 minus t, and z equals t. These expressions from your parametric solution, showing all possible solutions as t varies over all real numbers. This approach makes it easy to understand the entire set of solutions visually. The solutions from a line, plane, or higher dimensional shape in the space of variables. Each value of the parameter t gives a specific point on that shape. So, instead of just one answer, you get a whole family of solutions described neatly with parameters. In practical terms, if after reducing the system, you find one equation disappears or turns into a statement like 0 equals 0, it signals dependency. You then pick one variable as a parameter, often called t or k, and solve the remaining equations for the other variables in terms of that parameter. This way, you create a parametric from that captures all solutions. Using this method helps you see the big picture of dependent systems. It shows that these systems don't have a single solution but an infinite set of solutions that can be described with parameters. This makes understanding complex nonlinear equations and functions much easier because you can visualize the solutions as a line or a plane in space. It's like having a map that shows all possible routes instead of just one path.